Hey guys, so the problem that we'll be discussing today is from the recent Starters 12 and the problem name is another shortest path problem. So the difficulty level of this problem is easy and its prerequisites are none. Let's have a look at the problem statement. So you are in a grid of dimensions n into m. You are allowed to perform two types of operations. So the first one is go down, left, up or right for cost x, okay? And the second one is that we have to go diagonally down left, down right, up left or up right for cost y. So basically if we are in a cell, then we can go up, right, down or left for cost x, and we can go down left, down right, up right and up left for cost y. So basically these are the two operations given. You cannot exit the grid. So find the minimum cost of going to the bottom right corner from the top left corner. So we have to just go across the grid and we have to find the minimum cost for this. So let's just take a small example. Let's take, we have a grid of 2 comma 3. So, or let's say we have a grid of 2 comma say 5. Okay. So we have to go, we are currently over here. So we have to go to this cell, right? Now, what is the best way? So first, let us take some imaginary values of x comma y. So let's say we have x is equal to 2 and y is equal to 5. So now here, essentially, if you want to go diagonal, I will be using 5. So instead of 5, I can use 1 down and 1 right. And I will get it done in 2 plus 2 is equal to 4 cost, right? So actually over here, y is not required. So this is x and this is y. So over here, y is not required. So here, the easy way is that first we go down for cost 2, then plus 2 4, plus 2 6, plus 2 8 and plus 2 will be 10. So the cost of going from 1 comma 1 to 2 comma 5 in this grid is 10. So this was the sample case. Now let us directly proceed to the solution approach. So let's start the solution approach. So in this problem, we'll be mainly having three cases. So let's see what they are. So case 1 is where y is greater than or equal to 2x. So over here, we know that y is like, let's say these are two blocks in the grid. So cost y can be incurred when we go from this block to this cell, right? Now, if y is greater than or equal to 2x, what we can just do is go down once and then go right once and then we incur 2x the cost. And if y is greater than or equal to 2x, why not just use 2x, right? Because we have no limit on the number of operations. So we can just use 2x. So this is the first case. So in this first case, we will not be using diagonal operations, right? Because it's not needed. Everything can be achieved by the up down right left operation, that is x. Now let us see the second case. So the second case is thus y is between 2x and x. So over here a diagonal operation is definitely better. So here you can see this is a diagonal operation. So if we take two operations of right left up down, that is if we go right first and then up, then the cost incurred will be 2x. Whereas if we go directly diagonally upwards, then the cost incurred will be y. And as you can clearly see over here, 2x is greater than y. So basically y will be the smarter option, that is going diagonally. So that is case 2. And now what is case 3? Case 3 is that x is greater than y. That means going diagonally is cheaper. So let us see an example of this case. So let's see, we have a situation like this, that we are in this cell and we want to get to this cell. So over here, if we use the x operation, we are going to do one down and another down. So that is 2x. And if we use the y operation, then what we'll do? First, one diagonally to the bottom right cell and then again diagonally to the bottom left cell. So 2y. And as we can see, x is greater than y, therefore 2x is also greater than 2y. That means using this operation is much more cheaper, right? So this is the case 3. So let us discuss each of these cases one by one and let us try and formulate the cost for each of these cases. So let's have a look at case 1. So case 1 is that y is greater than 2x. That means using the x operation 2 times is still cheaper than using y once. So over here we have x is equal to 2 and y is equal to 5, which satisfies this case. And we have n is equal to 3 and m is equal to 6. This is the grid. Now we have to go from 1 comma 1 to 3 comma 6. So let us see what is the best path. So we go from here to here, here, and then directly over here without using any of the diagonal operation. So let us see what was the cost for this. So we used the x operation 1, 2, 3, 4, 5, 6, 7 times, right? So using the x operation 7 times, so 7 into 2, which is 14. So 14 was the cost for this grid. Now let us see how we can generalize this. So the answer for this grid will be, we are going from 1 to n and we are also going from 1 to m. So basically what we are doing is we are traveling n minus 1 vertically plus m minus 1 horizontally, and this is the basically distance we are traveling multiplied by the cost, which is x. So it is nothing but n plus m minus 2 into x. So this is the cost for case 1. Now let us see case 2. So let us see case 2 now. So again we start from the 1 comma 1 cell and we have to go to this cell. So here we have n is equal to 4, m is equal to 6, x is equal to 3 and y is equal to 5. So as case 2 suggests that y is between x and 2x, here exactly 2x is 6, hence y is between x and 2x. So here basically using the diagonal operation once is better than using once right and down. So basically diagonal is better than 2x's. Now over here the best move will be to use the diagonal operation as much as possible and then with the remaining operations to use the single direction x. So here basically our best course of action will be to go diagonal once, twice, thrice. So we went diagonal thrice and then we will go 1, 2. So we used y 3 times and we have used x twice. So basically the answer for this is 3 into 5, which is 15, plus 2 into 3, which is 6. That means the answer is 21. So for this case, the answer will be 21. Now let us try to again generalize this. So you can clearly see we can go diagonal only a limited number of times. And that is because the grid, so one dimension of the grid is smaller than the other. So here, since n was 4, we could go down only 3 times. So basically, the number of times that we can use the y operation is basically the minimum of n minus 1, comma, m minus 1, right? This is the minimum, this is the maximum number of times that you can use the y operation. So basically the cost will be y into minimum of this plus, now we had to use the x operation 2 times. So basically it is nothing but the difference in the dimensions, because that is how many times we had to use it. So basically plus m minus n. So m minus n over here, but it is basically absolute of m minus n. So this is basically the answer for case 2. So you can see this formula easily satisfies this. Let us try once that y was 5, and what is the minimum of n minus 1 comma m minus 1? It is nothing but 3. So 5 into 3 plus what is the absolute of m minus n? It is 2, sorry, into x. So yeah, 2 into 3. So we can clearly see it is 5 into 3 plus 2 into 3, which is 21. So we saw case 2. Now let us proceed to case 3. So in case 3, we have x greater than y. That means a single linear operation is costlier than a diagonal operation. So here we are going to try to minimize the use of linear operation as much as possible. So over here we again start from 1 comma 1 and we have to end at say 4 comma 6. So here x is equal to 4 and y is equal to 3. So let's see how we can do this. So here the best way is first go diagonal and get as close to the point as possible. So we use 3 diagonal operations first, and then instead of using 2 linear operations, what do? Is we use one diagonal, that is one up right operation, and then we use again one bottom right diagonal operation. So instead of reaching in 2 linear operations, we reached in 2 diagonal operations, right? So basically this is the whole point. So over here the answer is nothing but 1 2 3 4 5. So 5 into 3, that is 15. So we reached in cost 15. Now let us discuss a variation over here. So here we did not use the x operation even once. Now let us add one more column to this. So now our reaching point is no longer this, but it is here. So we will again use the same thing, that we will go 1 2 3 operations below, one top and one here. Now from here, how do we reach over here? So there is no way to reach over here using just diagonal operations, because these are cells of different parity, right? So here we have to use the linear, that is the x operation, at least once. So here the x operation will be used. And here you can clearly see that in case 3, the maximum number of times that the x operation will be used is 1. The x operation will not be used more than one time. So it will either be not used, that is used 0 times, or it will be used once. So basically this is case 3, and let's not try to generalize case 3. I will explain that in the solution approach itself. So yeah, now let us proceed to the implementation. So starting off with the C++ implementation, let us first take input the 4 variables, which is n, m, x and y. Okay, so caution over here that we have to use fast input and output over here. So because as it's written, the input output is large, so this is necessary. Also, you have to use long int because of the constraint. It may overflow the int limit. So that's there. So here we take input the 4 variables m, n, m, x and y. Now over here, we first set the precedence that if n is greater than m, we will swap n comma m. So in this question, we are assuming that m is always greater than n. That is why we are doing this. Now the difference is m minus n. So this difference is nothing but the difference in m minus n. So this is the minimum number of linear operations you will have to use in case 2. Okay. So now let us see case 1 first. So case 1 is nothing but x into n plus m minus 2. So this is the case 1 that we saw. Now the case 2 is y into n minus 1. So here we had seen that y into minimum of n minus 1 comma m minus 1, right? But over here we have already set that if n is greater than m, then swap. So we can clearly say that m is always greater than n according to our solution. Therefore we are saying that y into n minus 1 plus difference into x. So difference is nothing but m minus n. We don't need the absolute value over here because we have set m greater than n. So again, this is case 2. Now let's come to case 3. So in case 3, we are doing similar to case 2, that we are using the diagonal operation as far as possible. And then basically this operation is nothing but the linear operation. So why are we doing difference by 2? Because with the diagonal operation, we are jumping 2 squares at a time, right? So as we saw over here, we were jumping 2 squares at a time. So if we do difference by 2, that is the total number of jumps that we would have. But that is the total distance covered. But also we will take into 2 operations for that. So we are doing, this is the number of operations of diagonal that we'll use into y. So over here, if you see here, the difference was 3. Therefore, we used 3 by 2, that is 1, into 2 operations. So 2 diagonal operations were used. This was not used because it was not possible. So this is basically difference upon 2 into y, which is the cost of the diagonal operation. plus difference modulo 2. So here the difference was 3, hence one operation had to be used because 3 mod 2 is equal to 1. So difference mod 2, one operation had to be used into x, right? Because it's a linear operation. So this is case 3. So these are the 3 cases and the answer can be only in one of these 3 cases. Therefore, what we'll do, we'll just calculate LL answer is equal to minimum of case 1, case 2, case 3. And this will give us the correct answer. So yeah, this was the solution approach. I hope you understood it and let me know if you have any doubts. Thank you.